Hi, I'm Sujata Murty. I'm a postdoctoral scholar at the Woods Hole Oceanographic Institution, and I use corals and models to try to understand how climate changed in the past. And so in climate research, long data sets are really invaluable. They can help us establish a baseline against which to measure recent climate change. They can also help illuminate connections between various aspects of the climate system, as well as help us validate climate models. But the problem is that instrumental climate data is really sparse before the 20th century, particularly in the Indian Ocean. But the Indian Ocean is actually a hot spot in a warming climate, with warming rates exceeding those of other tropical oceans. And the Indian Ocean has actually been gaining a lot of attention recently for its role in the heat uptake and the redistribution of that heat. The Indian Ocean also strongly impacts the Asian monsoon with its seasonally reversing precipitation and wind patterns. And that monsoon system is a lifeline for 1 billion people. So small changes in monsoon precipitation or the extreme weather events associated with that will strongly impact those societies living in these Indian Ocean countries and Indian Ocean islands. So because direct measurements of rainfall and temperature and ocean salinity are really sparse in the Indian Ocean, we have to find other tools that can allow us to look at changes farther back in time than what we currently have with those direct measurements. And so the tool I use in my research are corals from coral reefs. And coral reefs are really great archives of past climate. They can grow continuously for hundreds of years at a time, and as they grow, they incorporate chemicals from the seawater that surrounds them into their calcium carbonate skeleton. And concentration of those chemicals in the coral skeleton will vary in relation to changes in temperature or rainfall or ocean salinity. And so we can start to use those chemical changes through time to look at past climate change for centuries and beyond. So to use corals, what we do is we go out into the field and we're looking for these massive boulder colonies that can grow up to 5 or 6 meters tall. So that's about 15 to 20 feet tall, or 500 or 600 years of continuous growth from this one coral. And so we go out into the field and we bring an underwater drill that's powered by seawater pressure, and we drill a cylindrical core through the center of the coral. We do this in about 1 meter long pieces at a time, so what we're left with are a bunch of pieces of coral that we have to bring back to land and reassemble kind of like a 3D jigsaw puzzle. But before we do that and before we leave the coral, we actually stick a cement plug in the hole that we drilled. And this allows the coral to grow back over and keep growing without hurting the coral at all. And so once we get back to land and we've reassembled our core, we have to cut a thin slab out of the middle of our core. And we do this so that we can X-ray it. Corals are a lot like tree rings. They grow annual density bands. And so we can use those bands that we visualize using X-rays to count backwards in time. So counting one band after another or 1 year after another back through time and assigning a specific age or time stamp to the coral material. Once we do that, we can subsample our coral by drilling tiny, tiny coral powder samples and analyzing those samples for changes in their chemical composition and relate that back to changes in climate over the lifespan of that coral. So in the Indian Ocean, we can use these coral records to reconstruct past changes in temperature, rainfall, ocean salinity, and even ocean circulation. But we can actually go one step farther and synthesize or combine these records with computer simulations of the ocean in order to not only ask the question, how has temperature changed in the past, but to also ask what's driving those changes. And this combined perspective and this broader perspective is what we hope will help us improve our ability to predict future changes in a warming world.